Okay, so now that we know how to use FEF files with EXAFS Neo, we can try and analyze the EXAFS of a simple system. So we activate our environment again. Change to the proper directory. And then we start the GUI. Okay, so we choose our data file, and here we're going to analyze the technetium data. We'll put our output file in the same folder. And for this, we'll use one FEF folder, and we've already calculated the technetium hexachloride data, so we have that there. So it doesn't recalculate it because it was already calculated. We'll do 100 generations because that's a good number. The population, number of individuals, best survivor percentages, those are things you don't have to change very often. Number of generations you do change, but 100 works for most cases. For the technetium, pass 2 and 3 don't play a large role, or for at least for the technetium hexachloride. So here we'll use 1, 4, and 5 as our paths. Mutations, don't really have to adjust much here, ever. This data is best from about K of 3.5 to K of 12.5. The best background subtraction parameters for this data set are RBKG of 1 and background K weight of 2. And then we can take a look at the effect of these parameters on the data. That's fairly reasonable. We can look at the data in K-space. That's very good. Stopping at about 12.5 because this glitch out here affects the higher order data. And then in our space we have one strong peak, and these peaks out here do indicate that multiple scattering does play a role in this system. So we're going to allow it to exit if it detects a steady state, and we're not going to create multiple input files. We're just going to do a single experimental run. When you're doing this for real, you would want to create multiple input files, but for speed and for this demonstration, it doesn't make sense to do that. So in the analysis window, this is where we'll look when we complete everything. And so right now we're going to run a single instance, and so we hit run. And then we'll start getting information popping up in this terminal window as it goes generation to generation. So here we can see that each generation is taking about 4 seconds, so that's going to take a while to do 100. But you can see it's trying to optimize all the parameters in multiple iterations as it goes through and through and through, searching parameter space for the best fit. So I'm going to let this run and stop it for a second. Stop the video for a second, and we'll come back when something more interesting is happening. Okay, I brought us back because we're now approaching the halfway point in the total number of generations. We're at on generation 46 right now. It has just completed 45. And when it gets to the halfway point, after it completes generation 50, it goes ahead and tries to optimize E0. So it'll go through, optimize E0, and then it will start the total optimization at the best value of E0. So here it's finished the first half, optimizing. It says E0 is about 1.16. and it'll hold that value for the next set of generations as it tries to keep improving. All right, we'll stop again, and then we'll pick back up when we're closer to the end. Okay, so here we've actually reached the steady state condition, which has stopped the calculation, stopped the search, and it then goes and optimizes E0 again, and it continued with the same value of 1.16. And now that it's complete, we can choose our output file and look at our results. So we have to choose the folder the output data is in and run the analysis. And now we can plot the K and R space spectra. You can see we get a very good fit to the data in both K and R space. It is fitting the multiple scattering because we did include a couple of multiple scattering paths. And it gives us information about the fitness score here. One interesting thing that our program does is it creates a LaTeX table. And what we can do with this is we can plot it and compile it. And you can see we get a nice table that contains all the parameters that we need to show in a publication. It shows the error bars, it shows what our values for each of the thing are, for each path are. N was from the FEF calculation, S0 squared, delta E0, sigma squared, R, the number of legs in the path, and it labels the path. So anybody can look at this and see what is necessary for the dissemination of information. In terms of publication plotting, we prefer to actually plot the individual K value, or the individual K space data from each of the paths. So we have the raw data, the GA fit, and then the data from path 0, path 1, and path 2. Now, these are not path 0, path 1, and path 2. These are actually the paths that were used in the calculation, and we recommend making a publication quality plot like this based on the output data. And I can talk about how to do that in our next episode.